Okay, so as I was telling you, there's going to be a Black History Month event for February. It'll be February 18th is the event from 5:30. I believe it's slated for an hour or an hour and a half. And if you're planning to participate, you can get 10 extra credit points. If you're just planning to attend, you'll get 3 extra credit points added onto your test scores. And if you're planning to participate, you're going to have to record a video of yourself and you want to upload it to this spot right here. So if you're going to submit your video, you want to click onto this link. And also, if you're planning to attend, you need to click onto this link to register. Okay. Again, it's worth 10 extra credit points if you sing, dance, rap, do a chemistry experiment, a poem. And you also are in the running for a prize. Top 3 will get a prize based upon your peers. So. And if you attend, you'll get 3 extra credit points. And I told Cassie that I would think about, because you can participate and attend, right? Or you could just participate and not attend. So I may give those people who decide that they're going to participate and attend 13 points. So I'm thinking about it right now. So I'll let you know for sure in a couple of days. And you guys all know how those points start adding up towards the end, right? Like, am I gonna get that A that I wanted, or am I gonna have to settle for that B, right? That's what you guys are all worried about last semester. Okay, so let's get started. Okay, so last we left off, let's see if you guys remember, how much you guys remember. So what is frequency? Mauricio. Frequency. Are you there? Anybody there? Can you guys hear me? Or am I just talking to myself?
I hear you.
I can hear you.
Okay. Okay, so Mauricio isn't talking. So we'll go with Angela. What do you think? What is frequency?
Isn't it some form of electromagnetic radiation?
Frequency?
Yeah.
No, it's not a form of electromagnetic radiation. Gamma rays is a form of electromagnetic radiation. UV is a form of electromagnetic radiation.
Oh, it's the number of wavelengths.
Number of wavelengths over a given point. Okay, your mic isn't working. Mauricio, can you hear me though? Okay, good. So Gracia, amplitude. What is amplitude?
What is what?
Amplitude.
Amplitude.
Yeah.
Let me remember what is amplitude. Isn't it like something, for example, like the wave, how it changes?
What do you mean by that?
When it changed to a single period, like for example the measurement. Oh my god, I don't know how to tell you.
So draw it on the screen. So what would be the amplitude of this wave right here?
How far, how long would it be?
So from
Is it the height?
the height,
Right? More of the height?
okay, that's right. So it'll be the height. It's half the height. That will be your amplitude.
Okay, the height.
Yeah, so from peak to trough, right? The distance from peak to trough. So that represents the amplitude. So when we're talking about radio waves, right? Radio waves have two forms. We have AM radio waves and we have FM radio waves, right? Well, AM radio waves is when you have a modulation of your amplitude. So your amplitude is modulating. So that height is alternating. It's variable, okay? FM radio waves is when your frequency is varying, right? So here you have a smaller wavelength, and so your frequency is going to be larger. You're going to have a larger frequency. Here you have a larger wavelength, so you're going to have a smaller frequency. Okay, and you guys remember wavelength is, let's say from peak to peak. Okay. Questions, concerns, Cash?
So amplitude is from peak to trough, and then wavelength is from trough to trough or peak to peak.
That is correct.
Okay.
So
what's frequency then?
It's the distance between peak to peak. What was
A
that?
point. The distance between a point. That's how I can tell.
So wait, what would you say for frequency then? It's
So
the same thing as
frequency-
wavelength?
So frequency is the number of cycles over a given time, right? So in this case, usually it's a second, right? So how many cycles can you get in a second? So that would be like your frequency.
I got a
So
question.
for instance,
Yeah, can I
that
have an
would be-
example?
one cycle, what was that?
I got a
No,
question.
nothing.
So that's 1, that's 2, that's 3, that's 4, that's 5, that's 6, that's 7, that's 8. So you'd have a frequency of 8 in that case over a given time. Let's say the time was a second. And then we're here, it's 1, 2, 3, 4. So cycles of you going up and down
Mhm.
over a period of time.
I have a question. I don't know if I'm wrong, but does this also have a maximum displacement?
What do you mean by that?
Well, I remember a little bit what I learned like for the first semester. I don't know if I'm wrong, but it was something based on the maximum displacement.
But what do you mean by that? What is being displaced?
It's it's more like how you said, like the distance moved by one point to the other point.
Okay, but what you got to understand, we're talking about particles moving in a wave-like structure,
Mhm.
right?
Yes.
And so, yeah, you can get displacement, but what are you displacing, right? So
Yes.
the relevancy in this context isn't,
Getting to that.
yes, but we are going to get to it in the sense of these things could cause events to happen. And so that's what we're going to try to build up to. And we'll get there.
Oh.
I think I understand what you're trying to get at, but
We're not there yet.
we're not there yet. Yes, there's a lot more that you guys need to figure out. Okay. If I'm understanding correctly, now I could be totally wrong, and it wouldn't be the first time. Okay, so let's keep moving. Okay, so we have interference patterns. So we have two types of interference patterns. We have a constructive interference pattern and a destructive interference pattern. So when two waves kind of collide with each other, they can interfere with each other, right? a destructive will kind of cancel each other out. So if these are light waves, you'll get dark regions as a result of that. Okay. Now, if it's a constructive interference, then you're going to get a brighter region. So you're going to get your brightest regions in those parts where you have overlap between the two waves that are both peaking, okay, or both troughing. Okay, so if one is peaking and one is troughing, they kind of cancel each other off, right? But if they're both peaking, then you're going to get a bright structure. Make sense? Have you guys noticed the change in flashlights? Like a long time ago, you would just get a flashlight that had that one little bulb in it, and that's it. You guys remember that? Back in the day when, you know, caveman roamed the world. Yeah, no, maybe.
I just used my phone flashlight.
You just
I
use
don't know
your
if I've
phone
ever actually
flashlight.
owned
For
a
the
flashlight.
thing, yes, I remember when I was little, would have those flashlights. They would only have like one light bulb.
Yeah, but if you look at the flashlights today, all of them are LEDs. And so they'll all have like, you'll have like 5 or 6 different LEDs in that single bulb. If you unscrew it, each LED gives off its own light. But what makes it so bright is the fact that they're all constructively interfering, right? So you get a much brighter signal as a result of all of those LEDs, right? You guys
Yeah.
kind of understand that?
Yeah, they also have Bluetooth.
Did you say they also have Bluetooth?
Yes, there's one that my uncle has, and it has Bluetooth.
Oh, okay. Okay, so here, this is just a figure basically showing you that interference. So those dark regions here, that would be constructive or destructive. Let's see, Taylor, constructive or destructive?
Destructive.
Okay. And then the bright regions.
Constructive.
Okay, simple, right?
Mm-hmm.
Okay, so not all waves are traveling waves. Some of them are kind of stationary, okay? So their stationary waves are standing waves, and the way they basically work is that they have endpoints or nodes, okay? So, and these waves are considered to be one-dimensional, right? Because they're only moving in one dimension in that case. So you guys did you guys play jump rope? Yeah, no, maybe? I think I asked this yesterday. You did?
Yes. Yes, I did. It was really fun.
It was really fun.
I still do.
You still play jump rope?
Yes, with 4 people at the same time.
Okay. So, but you guys, did you guys ever just kind of whip the rope up and down, back and forth? So it just kind of made a wave like.
Oh, yes. Yes.
Okay. So that's essentially what's happening here, right? So if we, just get a little bit of a whip, one person here, these guys are your endpoints. Okay. So this here, these guys would also be called nodes because they're not moving in this context. Okay. So you have nodes at your endpoint. Okay. So here's an example of a wave. So in this case, this guy would have like an integer of association 1. This guy would have 2 because you have a complete wave. So a half of a wave counts as an integer of 1. A complete wave counts as 2. So how many would this guy have?
3.
Yeah, 3 little humps, right? I can count. And then this guy?
4.
Okay. So now this is an example of quantization because in this case, you guys have a point where there won't be a wave, or it's not making that wave structure. It doesn't have that arc. It has like that center point. So it's quantized. So we're able to sit there and segregate it into very discrete lines, right? So here, that would give us a wave structure. Here, that would be like a point. Here, this would be a wave structure. That would be a point. So that's kind of like steps. So we're able to sit there and have complete steps, like steps on a stair or something like that. Individual steps instead of a walkway that just went straight up. Okay. Okay, so as I said, each of those kind of represents like an integer, right? And so when we're talking about the waves that are associated with light, they actually, it's a form of quantization as well. So you're going to get discrete patterns, particularly when we're talking about chemicals. And we'll talk more about that here in a minute. Okay. So in the case of like sound waves, right, or harmonic waves. So anybody play the piano? No? Anybody play the violin or the guitar?
The saxophone.
The saxophone?
Yeah.
I listen to
Not-
people who are more artistic than me play those
Oh.
instruments.
Oh, okay.
I used to play the clarinet.
Used to play the clarinet.
Yes.
So on the string instruments, it's kind of like you get notes, right? Because you get vibrations of the strings. Isn't that what causes the sound to occur? Yeah, no, maybe?
Yes.
Okay. So in that context, you know, depending on how you have your string tightened and everything like that, you can get a lot of waves happening, or you can get a few waves happening. And then as a result of those notes, you get different sounds, right?
True. Yes.
So we can also have a case where we have two dimensions. So that's an example. All of that before was an example of a dimension. Now we can also have two-dimensional waves. So the two dimensions that we're going to be talking about are going to be radial or circular and angular, right? So here on this this Sander table here, you're getting some vibrations going on, and as a result of it, you're getting a radial node forming. And so you're able to get those very defined circles of sand as a result of that, or powder, okay? And so beautiful circles perfectly, right? Now, if we also add a layer of waves going in the other dimension, a second dimension, we'll end up with angular nodes. Angular nodes are angles, right? So this is a combination of the circular node or the radial. And then this is the example of the angular. Okay. Okay, come on. Okay. So black body radiation. So sunlight is basically, or white light is a continuous spectrum, right? Yeah, no, maybe.
Yes.
Yes. So do you guys have your diffraction slides still in your kits? Oh, none of you guys still have your kits, right?
I have
Oh
mine.
yeah, you can see different type of colors depends on the light.
Uh-huh. So if it's white light, you get a nice, beautiful, let's see if you guys can see.
Oh yeah, a rainbow. I can see a rainbow. Wait. Oh yeah, I can see like yes.
Okay.
Blue, white, yellow.
Yeah, so that's an example of continuous spectrum, right? And so the wavelengths kind of feed into each other. Now, a black body is basically it's like an emitter that is going to behave on the heat of material, on heated material. Okay, and so as your temperature goes up, it's going to have an effect on the system, right? So as temperature goes up, what do you think is happening in terms of energy? Are you going to be increasing in energy, or are you going to be?
Increasing energy?
Okay. And in the case of that, so as temperature goes up, so do you think your wavelength is going to get smaller, or do you think your wavelength is going to get larger? Now, we kind of talked about this yesterday. And let's kind of put this in perspective. So we have energy is equal to, I don't know what I'm doing there. I'm putting the equal sign in an E at the same time. It's been a long day. We have energy is equal to, how can we relate energy to frequency? What is that equation? Anyone?
Would that be the one for kinetic energy?
So that would be,
One
there's a
half
couple of
mv
them, right?
squared.
1/2, I'm doing it again, 1/2 mv squared. So, but V is velocity, not frequency. So how can I
Right.
relate it to frequency? You guys remember that one?
Are they directly proportional to one another?
They are directly proportional to one another.
Okay.
And so do you guys remember the equation?
I do not, but I just know that they're related.
So they're directly proportional to each other, and we use Planck's constant times nu.
Mm.
It was just on Monday. It wasn't too long ago. Okay, so, and how does nu relate to wavelength when we're talking about light?
Oh, you were talking about lambda too.
Lambda. Okay, so we have lambda times what? Equals what? Anyone remembers?
Is it times frequency?
Yeah.
And that equals the wavelength?
Does it equal the wavelength?
I
Lambda
don't know.
is the wavelength.
Oh, no. Wait a minute. So then it would equal, I don't know what it's called.
Light. Think about light.
I was gonna say it would equal the velocity, but I knew that wasn't.
Wouldn't be wouldn't be
But you're kind of close.
C?
Wait. You're kind of close. Not velocity, but it's not V.
I just remember the letter.
It's
What
just
is the letter?
C equals and then lambda.
Okay, C equals lambda times V. What is C?
the speed of light, yeah.
Okay. Whew, this is gonna be a rough semester, it looks like.
And then nu equals FR.
Frequency. Yep.
Yeah, frequency.
Okay. So you said as temperature goes up, that kind of means energy is going to go up. So do you guys think in the case of temperature going up, are you going to have a smaller wavelength or are you going to have a larger wavelength?
Larger?
Small?
I think you're gonna have a small.
Yeah, I think
Okay.
smaller.
Okay. So let's look at this. Frequency nu equals so nu equals C over lambda, right? If we plugged in C over lambda for nu, so we get this equation here. And H is just Planck's constant, the constant. I'll give you the value here in a minute. And that. Okay, so as energy goes up, lambda is going to do what?
Decrease.
Lambda is going to decrease. So that means that the wavelength is going to get smaller. That distance from wave to wave is going to get smaller. Okay. Okay. So here, this is basically just shows you the sunlight. This is a black body spectrum at 520 or 5,220 degrees Celsius. Okay. And so in that context, the black body spectrum would fall into about here, it falls into the visible light range. Okay. Below the wavelength, that black body spectrum would be in the UV region, and then that would be the infrared. Okay. So clear. I'm going to keep this. Get rid of this because we don't need it right now. So in the case of the maxima, or the largest wavelength, the maximum wavelength, so if we shift to a shorter wavelength, your temperature is going to increase. If we go to a larger wavelength, your temperature is going to decrease. Okay. Come on. So wavelength, this is going to be our intensity, and this represents our temperature. So at lower temperatures, the peak or our maximum wavelength is going to be at a larger than at higher temperatures. Okay, so this is about what, 5 micrometers? I mean 0.5 micrometers in this case for the peak, the highest point at 600 degrees Kelvin. And then at 300 degrees Kelvin, the wavelength increases. So as temperature increases, which also means that energy is going to be increasing, then your wavelength is going to decrease. Okay, make sense?
Yes.
Good. So tell me about intensity. Tell me about frequency. What happens to the frequency? So as temperature increases, what is going to happen to the frequency?
Wouldn't it decrease?
As temperature increase? Are you sure?
No. No, I'm not sure. Wait.
Okay.
Wait. Wouldn't it stay the same?
It's going to stay the same? Are you sure?
What's the question again?
So what happens to the frequency as temperature increases?
Would it be? It would be smaller, but it would still be longer. No, so increase
It would increase.
because like the waves would be like smaller but longer. No.
And it would be higher, like it would increase.
Okay, so somebody says it would be higher, somebody says it would be lower, somebody says no effect at all. Okay, so let's do a poll, and then I'll tell you the answer. Okay. Okay, and poll, share results. So we always have to have that rebel, right? So the correct answer is frequency is going to increase as temperature increases. Think about it. Energy and frequency are directly proportional. Here, energy and frequency are directly proportional. H is a constant. H is always going to be the same thing. So if energy increases, temperature is increasing, your energy is going to be increasing. So then that means that your frequency is also going to increase. But lambda is inversely proportional to energy. So as energy increases, lambda, or the wavelength, is going to decrease. Right? Yes, no, maybe?
Yes.
Okay, good.
I just figured if you heat something up, it moves faster, so.
Yeah. And then that also means that it's exerting more energy, right?
Yeah.
So it's kind of like if I have this bottle of water, right? And then I just start heating it up, just really heating it up and heating it up and heating it up and heating it up, what's going to happen over time?
Explode.
It's going to explode. And this cap is going to come off at a lot of kinetic energy as a result of that, right? Because you're building up that pressure. True?
Yes,
False?
that happened to me in the morning.
Okay. Good. Okay, so Max Planck's constant, he basically came up with that equation that we basically were talking about. And his whole theory was kind of revolving around black body radiation when he designed his equation. Okay. So he basically said that, of course, he believes that energy is quantized. So then that means that there's going to be levels of energy, and those integers and direct integers. But basically, E is going to be equal to Planck's constant times nu, which is the frequency. This is nu, not v, not the velocity. I think when I was writing that, I couldn't find my nu. But, okay. So this is the value of Planck's constant. It'll be provided for you, but if you can remember it, it's great. If not, don't worry about it. But you need to know how to use it, and you need to know what that h is, because I'm not going to tell you it's Planck's constant. I'm just going to write Planck's constant equals oops, I go too far. Okay. So this kind of starts dealing with the photoelectric effect. So you'll notice there's a lot of paradoxes, particularly in this area in quantum. And so all of these guys are going to kind of be contributing to each other, and then they're just going to keep taking credit for it. So one of the paradoxes basically is going to be resolved by that photoelectric effect, right? So that concept of electrons emitting light, right? And so if a metal is struck by some energy, electrons could basically be removed from that piece of metal. And then as those electrons are removed from that piece of metal, right, they're just flying off. As those electrons come back down, they're going to emit light. Okay. So first part is those metals have to absorb energy, right? And so if they're absorbing energy, they have to have enough energy to have those electrons released. If there's not enough energy to have those electrons released, they won't be removed from the metal. So that's the first thing. So if I have enough energy to release an electron, I can get an electron going at a certain velocity, right? If I put a whole bunch more energy in there, I can speed up those velocity, and I can also speed up the number of electrons that are going to be released. Okay, so there's what is called like a threshold of energy that's needed to be absorbed. And so if we're talking about the threshold of energy, is there a frequency that needs to be absorbed to have electrons released? Yeah, no, maybe?
I believe yes.
You believe yes. So yeah,
Yes.
so because if there's a threshold energy, there has to be a threshold frequency, because energy is directly proportional to your frequency. Okay, so now that we've kind of talked about that, right? So if I have a low frequency a low frequency, that basically means a high wavelength. Right? Is that true?
No.
No, it's not true.
Well, like all the time, or it could not.
You tell me, are they proportional? So here's frequency, nu, and this is lambda, that's wavelength.
No.
So if I have a high wavelength, am I going to have a low frequency?
Mm.
Yeah.
Let's put numbers in there, because that's the way it works. Okay, so we have the speed of light. We know the speed of light is a constant, right?
Yes.
So speed of light is 3.00 times 10 to the 8 meters per second. Okay, so that's a constant. That's always going to be, 2.998 times 10 to the 8th or 3.00 times 10 to the 8th. It's always going to be that number. Okay, so that isn't going to be changing. That's always going to be the same. So if I have a wavelength that is 400 nanometers, 400 nanometers is 4.00 times 10 to the minus 7 meters. So then my wavelength is going to be what? Anybody there?
It's gonna be bigger than your frequency.
Well,
Right.
no, our frequency, this is our frequency. We're solving for our frequency. If we have the wavelength, our frequency is going to be what?
Smaller. Oh, I don't know. I didn't hear the exact number.
7.5
Is
times 10 to the what? 50 times 10 to the 15th, 14th. And that's 1 over seconds. Okay, so 7.5 times 10 to the 14th. One over seconds or hertz. Okay, so again, our wavelength, our speed of light is constant. Let's say we change our wavelength to, let's change it to 800. So then that's 8.00 times 10 to the 7. 10 to the minus 7 meters. So is that number going to be bigger or smaller than the 7.5?
wouldn't be smaller.
Going to be smaller, right?
Yes.
So it's going to be half that, because what? I said half. I said 8. So 7.5.
It would be 2. Yeah.
So it'll be 3.75 times 10 to the 14th. If we made this, instead of 800 nanometers, we say 1,000 nanometers, it's going to be even smaller. So as my wavelength increases, my frequency decreases, right? Yeah?
Yes.
Okay, so they're
Yes.
inversely proportional to each other. Anytime that you see an equation where this guy here is equal to 1 over the other guy, they're considered to be inversely proportional, the inverse, right? You guys have heard of the inverse, right? Yeah, no, maybe?
Yes. Yes. Yes.
Okay, so These guys are inversely proportional. So as frequency increases, wavelength is going to decrease. Now, if you need a threshold frequency, so you need a frequency that's going to be high enough to allow electron to be removed. Okay, so if I have, let's say, I have a frequency of 400, right? And it doesn't meet the threshold. I mean, not a frequency of 400, a wavelength of 400 nanometers. It doesn't meet the threshold. It's just below that threshold, right? It's that borderline, okay? So what frequency would allow us to meet, I'm sorry, not what frequency, what wavelength would allow us to meet that threshold? One that's greater than it or one that's less than it?
Right.
So if I go to 900 nanometers, is that going to allow me to meet the threshold? Yeah, no, maybe.
Are we comparing it to the 3.75?
We're
It would
comparing
be,
it to,
it wouldn't be yes because it's bigger.
so you say yes. Okay. Okay,
It would be
so
higher.
if energy is directly proportional to the wavelength, I mean, not the wavelength, directly proportional to the frequency, right? Energy is directly proportional to frequency. Now, if we're increasing our wavelength, is that going to give me more energy or is that going to give me less energy?
More energy?
But it's going to give you less energy.
So a higher wavelength will give me less energy or a lower energy?
Oh no, a high one? No, it would give you more energy.
A high wavelength is going to give me wavelength, lambda. Look at the equation.
Yes, lambda.
It will give you less.
E equals HC lambda.
It'll give you less because they're inversely proportional.
That's right. It'll give me less because it's inversely proportional. So if there's a threshold energy, right, meaning that there's a minimal amount of energy that is needed to release an electron, you need to be sure that your wavelength, is it going to be a high wavelength or a low wavelength? Relative to that threshold energy. Or that threshold.
And I was right the first time then.
Yes, because since they're indirectly proportional, you want this guy to be small, right?
Mm-hmm. Yes.
So that you would have enough energy to sit there and get released. Okay, so I'll show you an example here in a minute. Okay, so I'm going to kind of erase this to kind of clear it up so that I'll stop getting myself confused here. Okay, so Einstein also played a part in that, and he also recognized that, hey, Planck was right about the quantization. And Einstein basically had said E equals mc squared and all that stuff. And then he also made a comment and he says, you know, when light hits a piece of metal, you're going to get a wave or a photon instead of just a particle being released. So he just kind of validated everything that everybody else said, because remember, they were talking about the wave particle duality. So you get in a combination of both, which he refers to as the photon. Okay. So Einstein just played with Planck's constant. He actually used the speed of light and all of that and plugged that into the equation. And he basically just showed that energy is indirectly proportional to the wavelength. Okay. Where energy is directly proportional to the frequency. Okay. So he also continued to play with this a little bit more. And here we have a larger wavelength, right? Larger wavelength hits the surface. No electrons are emitted. They're not released, they're not ejected, because there's not enough energy to inject them, because your frequency is low. As you decrease your wavelength, you get higher frequency, and you're able to eject electrons. And as you get your wavelength gets even smaller, you're able to eject electrons faster. So the speed of ejection will increase as the wavelength decreases. Does that make sense?
Yeah.
Okay, I'm getting it.
Okay. So in other words, you have to have that threshold energy met to allow electrons to be released. But if you have a higher wavelength means lower energy. So now thinking about this, right? Thinking about this whole spectrum of radiation from gamma to sound waves. Which one is going to have the most energy associated with it? Gamma or infrared? Who's going to be higher in energy? Gamma rays or infrared?
Would it be gamma?
Okay. That is correct.
I don't really know where infrared is on the spectrum, so I'm just guessing.
You guys didn't pay attention. Did you even look at the slides?
I looked.
You looked. Gamma, infrared. Okay.
So yeah, definitely gamma.
Okay. So in terms of who's going to have more radiation associated with it, or who's going to have higher energy, radio waves or microwaves?
Microwave?
Microwaves, right? Can you sit your food next to the radio and say, okay, heat up?
No.
No, you can't, right? So
No.
that kind of makes sense. Microwave is going to have more energy associated with it, right?
Yes, because of the waves.
Okay, so now whose frequency is going to be higher, microwaves or radio waves?
Radio waves. No?
Frequency.
Yeah, because it's like further away.
Microwave.
Frequency meaning the little peaks. Can you get a whole bunch of little peaks? Who's going to have the little peaks? Who's going to have more little peaks? Microwaves or radio waves? Look at that.
I would say radio.
Okay. So here are radio waves. In a given piece, given time, you have 1, 2. Here are microwaves, right? So if we do that same one, we have 2 of them in that same distance where we'd have. So do you see the difference? So frequency is going to increase in this direction. Wavelength is going to increase in that one. Radio waves have a larger wavelength, so it's going to have a smaller frequency compared to microwaves. Okay. Does that help? Are you guys there? Are you falling asleep on me?
Yes.
At least you're honest.
No, I'm talking that yes, I pay attention. Yes, microwave.
About the microwave. Okay. So when we see light from a neon sign, we are observing radiation from excited neon atoms. If this radiation has a wavelength of 640 nanometers, what is the energy of the photon being emitted? So what are we going to use? How are we going to calculate the energy?
You convert the units.
So what do you mean by that? So I'm going to 640. What am I going to convert it to?
To
And what does that represent? That 640.
Nano. I mean, wavelength.
It's going to be a wavelength. Okay.
Mhm.
So we're going to convert it to what units? And what is the equation we're going to be using to solve for energy? That's right. That's right, Mauricio. So E equals Planck's constant times C divided by nu. I mean by lambda, not nu. And we're going to convert meters into our lambda, meters into, nanometers into meters. So how many nanometers are in a meter?
Is it 10 to the 9? Or, yeah, 1 times 10 to the 9.
10 to the 9th nanometers. Oops. Okay, so then that's 6.4 times 10 to the minus 7. Okay, Planck's constant is 6.626 times 10 to the minus 34. And that's joules per second. And the speed of light is what?
Three 3.0 times 10 to the 8th.
Okay, you guys need to start drinking some coffee at night to help us through this. Maybe a little whiskey to go along with it to loosen you up. Oops. Yeah. Okay.
I'm almost 21, so yes.
Okay. So you'll get 3.10 times 10 to the minus 19th joules. And actually it should be 3.1 because there's technically only 2 sig. So my typo, my bad. Questions, concerns, Cash, credit?
I like those two parts.
Okay. Simple, right? Just conversions, plug and chug.
Oh, yes.
Okay, so now we talked about the continuous spectrum, right? So scientists have basically found that, certain solids, certain liquids, and certain gases, they basically are able to emit light, right? They can absorb that energy, electrons inside, and they can come back down, but they have very discrete line spectrums, okay? So compared to those continuous spectrums, we have these very narrow line spectrums, and they're emitting various certain colors and certain wavelengths associated with those colors, okay? And so here's basically a neon sign, right? So in this case of the neon sign, depending on the amount of energy you put in, you're exciting the electrons to a certain level, so you're getting a certain color emitted for each of the different neon signs. So depending on how much energy you're putting in that particular part of the neon sign, you're going to get a certain color emitted as a result. Make sense?
Yes.
Okay, good. So now energy. So we're putting energy in. What is that energy doing? What was that, Jess?
Is it the first thing that comes to mind is like the law of conservation for some reason? Like energy,
Okay.
you can't create energy or destroy it. It's always being.
Okay, so we're putting energy in that system. We're putting energy, and it's going into that neon electron. And what is happening to that electron?
They're moving like crazy.
Being excited.
It starts to get excited and it starts moving like crazy, right? So it goes up. How many of you guys eat a lot of sugar, like during Halloween, or have kids and they just eat their whole bag of candy?
I mean, that's me year round, but yeah.
That's year around. So by the end of the night, what are you doing?
Not feeling too
Eating
great.
Snickers.
Make YouTube videos, you know, talking to people.
Eating
Okay.
Snickers.
And then eventually, right, you're going to go up, you're going to go up, you're going to go up, you're going to go up. And then what's going to happen?
You crash hard.
You crash hard, right?
Yes,
Well,
when
that's
you
exactly
gain
what's-
weight, oh, it's so hard to lose it.
Okay, so that's a whole nother subject there. We'll talk about that in biology, okay? So the sugar makes you get a real good high, right? And so you go up, you're on high on energy, you're like, pumped, right? Yeah. And then you're just, right? Okay, so that's exactly what's happening to these electrons. So in the case of our neon sign, we put energy in, we excite that electron, it goes up, and then as it comes back down, it emits light, and we get that light that we see, okay? Are you with me?
Yeah.
Okay,
Yes.
good. Oops, I got carried away. Okay, so in the case of line spectra, so each element, right, has the ability to do this, right? So for instance, we have sodium here, right? So this is the line spectra for sodium. So we're putting energy into those electrons that sodium has, and then it goes up, it comes back down, and so we get all of these different colors as a result of how much energy is being absorbed and how much energy is being released because of the law of conservation. What goes in has to come back down, right? It has to come back out, okay? And the way it comes out is as light energy or light that we actually see, okay?
When it comes down.
When it comes down, yeah.
That's
So we
nice.
put the energy in, it brings it up, and then as it comes back down, it emits light. So you excite it, and then it drops down, and then you get light emission. Okay? Are you with me? Okay?
Yes.
Yeah.
So I thought you were going to say whatever
How many
goes
electrons does
in,
hydrogen have?
gets
How many electrons?
How many electrons does hydrogen have?
You?
One.
one.
One? Okay.
Okay, that's right. Hydrogen has one electron, right? So, but we have 4 different discrete lines. Why do we have 4 discrete lines if we only have one electron? Anybody want to take a guess?
I have no idea.
That it gets excited.
It's a gas. I don't
So
know.
it moves around, kind of like when you eat sugar, you're excited, so you're moving around. No.
No, not quite. You're treading on the correct answer there. Okay, so
The
if
fast
you
you can get them going.
okay, so if you eat a pound of sugar, that's going to give you one amount of energy. If you eat 2 pounds of sugar, then that's going to give you another amount of energy. And then if you eat 3 pounds of sugar, okay, so but each of them are going to give you a very discrete amount of energy, right?
Mm-hmm.
Is that true? So in other words, I can, if I put enough energy in you, I can excite you to a much higher level.
Speed of light.
Okay, so that's what's happening. You have that electron being excited to multiple levels. So remember when we were talking about those integers, those 1, 2, 3, 4 integers?
Mm-hmm.
They represent
Mhm.
levels, right? So
Yes.
those electrons can be excited to different levels.
So those different lines are representing different photons hitting it in every case?
Yes, so it's different amount of energy exciting the electrons to allow the photon to get in. Yes.
Mhm.
Okay, and we'll talk about that here in a second, but I want to show you something first. Get there. So remember when we were talking about those numbers on the side coming down here?
Yeah.
So these guys, these represents those integers, right? That 1, that 2, that 3, that 4. Those represent energy levels. So in theory, that one electron that hydrogen has, it can be excited to that second energy level. So it can be at the space where the electron for lithium is at, right? And then it has to come back down. And then it can get excited to that third energy level, and then to the fourth energy level. So the periodic table actually lets us know about the energy levels too, right? So they technically can be excited to those other energy levels. Okay, so come on. Okay, so Balder basically had derived this equation, and he said that 1 over the wavelength is equal to k times, and in the case for hydrogen, and he only did it for hydrogen, since there were 4 visible lines being emitted, he says 1/4 minus 1/2 n being the whole integer. But they were starting at the third level. You know, he randomly said 3, you know. And the thing is that he had made the assumption that that 4 represented 4 distinct lines, okay? Now, later on, Ryberg, he basically said, okay, you know, Balder, you know, he wasn't thinking quite right, so I'm just going to take over the equation, and I'm just going to call it Ryberg's equation and give it the Ryberg constant, right? And so he said, okay, so we're going to use the Ryberg constant, and those integers, right, they represent the energy level that the electron is being excited from, okay? So, and in that situation, you always had your equation so that your N1 is always going to be, it's always going to be less than your N2, right? And that kind of makes sense, otherwise you end up with a negative number, okay? So, and that's going to be equal to 1 over the wavelength. So then Bohr came along, and Bohr was like, you know, okay, so we kind of have to abandon our classic thought of physics, right? Physics, classic physics basically said a particle or a light, but you can't have a combination of both, that dual strength theory. And then he said, well, you know, there's some other aspect of it, that dual mentality that we have to sit there and think about. One of the major things that he basically said was that in the case of an atom, you have the nucleus, right? And then you have electrons that are continuously moving around the nucleus, kind of like the way planets move around the sun, right? So I have a question for you. Does Venus, so we have Mercury is the closest to the sun, is that correct? And then it's Venus, and then it's Earth, right? Aren't we the third planet?
I know we're the third, and then Mars is the fourth. That's all I know.
Okay. Yeah, third rock from the sun, right? We're the third planet, right? Okay, so Mercury be the first, Venus is the second, Earth is the third. Does Venus ever go outside of Earth and become the fourth or make us the second?
Yeah, Venus
No.
gets closer to Earth.
It gets closer to Earth, but does it go beyond the Earth? You understand what I'm saying? So,
No.
No, it doesn't go beyond.
yeah, okay. So that's the sun. That's Mercury. That's Venus. Oops. And there's the, although I have them overlapping, they're not really overlapping. And, oops. There's the Earth. Maybe. No, it does not want to let me write. There we go. Okay, so that will be the Earth's rotation. Okay, so this guy never goes over us, right? It kind of orbits around.
Yes.
Okay, okay, that's good. So everybody kind of maintains their orbit. So now what Bohr was basically saying was that the atom is kind of like this. So in its natural state, when it's not been excited or anything like that, it's like this. But when you excite the electron, so let's say this is the nucleus, I'm going to make it a different color. Or equivalent to the sun, make it a solid. Okay, there's our nucleus. So Bohr says, well, normally that one electron just orbits that nucleus, right? But if you put enough energy in, you can kick that electron to that next orbit. And then it'll be in this orbit for a bit until it loses that energy and drops back down. So this here represents its ground state. This represents its excited state. So depending on how much energy you put in there, you can kick that electron further out. You put a lot of energy in there, the electron escapes and gets further out. Then it orbits, and then it drops back down. Okay, are you with me?
Mm-hmm.
Good, good. How we doing on time? Okay, so okay, so now when he did this, now we're going to say, I'm going to tell you the end of the story before I tell you all the rest. Now for the hydrogen atom, that worked out perfectly, right? It was just like incredible. Everybody's like, damn, this guy is so damn smart, right? And then he started trying to do other atoms and it didn't work out so well. Okay, and we'll talk about that, why that's the case here in a minute. Okay, so he also said something else. He said that, you know, it had a ground state. When it's in its ground state, it's not going to be emitting radiation. And that kind of was against all of the other things that were being said. Can you guys hold on 1 second? I'm getting a message from Kalinga, so that's probably bad. Okay, sorry about that. We're in the last 10 minutes, last couple of slides. So let's talk a little bit about the Bohr hydrogen atom. So can you guys see my screen?
No.
No, okay.
No, to be honest.
Okay, can you see it now?
Yep.
Okay, good.
Yes.
Okay, so Bohr basically kind of incorporated everybody's theory. And he said, well, we're going to take Planck's quantization ideas, and we're going to take Einstein's, the concept of being a photon, and it has to do with the energy, and it's that change in energy that we're going to be looking at, right? And so he made this modification to the equation. And he said, we're going to be looking at the initial orbit energy and the final orbit energy. So we're looking at the difference between them. And so then he further made this valuation where he used the constant K and represents that energy state. And then he went a little bit further and said that the delta energy is going to be equal to K minus the wavelength. And then basically he comes up with this. And then as you guys take a look, Ryberg's equation is essentially the same equation, this part here, and that's just the Ryberg's constant. Okay, so then he actually did this experiment. He did all the measurements, and he found that this is ground state for that hydrogen atom. And then as you increase the energy to that first level, right, that would be the amount of energy that would be emitted. Then the second level, that next level, I'm sorry, the increase the energy from integer 1 to 2, from 2 to 3, and from 1 to 4. And so by using the excitation or inputting that energy in there, you're able to sit there and get it to that next energy level. Okay, and so basically the lowest energy level in 1 was your ground state, and all of the others represent those higher states. Okay, and so this explains the different spectra. So that explains the different lines. So each line represents a different amount of energy. So which one would be the lowest amount of energy? We go back to the spectra for hydrogen. Which one is going to be the lower energy? The red or the purple?
The red.
That's right.
Would it be
That's right. The red is going to be lower in energy because the wavelength is bigger. That means that your energy is going to be smaller in that case. Good job. Okay. Okay, so again, the atom is able to sit there and absorb energy as photons, and then that gets the electrons excited. And so then they're shot up into higher orbits. So, you know, you're thinking about that metal or that atom itself, it absorbs that electron, shoots that electrons up, but that electron is still going to be orbiting that atom, but it's going to drop back down. So eventually it's going to drop back down and you're going to get light emitted as a result of that. Okay. And so here, this is basically showing that electrons are being excited. They shoot up to different energy levels and then they drop back down. Also, if they're at different energy levels, they could be excited some more to another energy level, but eventually it has to drop back down. Okay. Piece of cake. So what is the energy in joules and the wavelength in meters of the light in the spectrum of hydrogen that represents the movement of electrons to the Bohr orbit n equals 4 to the Bohr orbit n equals 6? Okay, what part of the electromagnetic spectrum would you find this radiation? Okay, so in this case, we're going to say energy, the change in energy is going to be equal to K, 1 over N1 squared minus 1 over N2 squared. So this is going to allow us to calculate the energy, right? So we just put in, for what is our N1? 4 or 6?
Would it be 4?
That's right. So N1 is going to be 4. It's going to be the smaller number. So we put in 4 for N1, 6 for N2. And so we're going to end up with an energy of 7.5 times 10 to the negative 20. And so then to calculate the wavelength, then we can just use E equals HC divided by lambda. And so we know the value of the energy. And so we just solve for lambda, right? So we get, this is our equation, lambda equals H delta E. And then we just plug and chug. Oops. So Planck's constant, 6.62 times 10 to the negative 34 joules per second. Joules seconds. And the speed of light, which is 2.998 times 10 to the 8th, or we could say 3.00 times 10 to the 8th. So seconds are going to cancel out, joules are going to cancel out, and then we're just going to be left with lambda meters. And so we get 2.626 times 10 to the minus 6. So if we go and use this, that's going to be roughly, what is that? 2,226 nanometers. So if we go back to the spectra, boy, we've been moving. Okay, so that would be 700 nanometers. So then we're looking at 1, 2, 3. So somewhere in this range right here. So it looks like it would be in the infrared area. It's 10 to the. Okay, questions, concerns, cash, credit, or did you already tap out?
Debit.
Debit? Okay. Okay, so as I said, Bohr, there were limitations to Bohr's model. It didn't work for helium because helium has 2 atoms. So it worked great and it worked perfectly for hydrogen because it only had 1 atom. So what happens when you have 2 atoms? It makes things so much more complicated. And then that was the problem. So this is where we're going to stop. Do you guys have any questions?
Not me.
No.
Okay, so now when I ask, because the first thing I'm going to ask you, so 1B, is why doesn't Bohr's atom work for anything other than hydrogen? Somebody had a question. Oh, no, I don't have any questions. Okay, so you guys go and get some rest so you guys will be ready for next week.
Oh, Dr. Hernay, I didn't have a question about the lecture, but I just wanted to make sure that on Friday, like the instructions that you had, we're gonna make a sign and then show up to the parking lot, like in the I like by the health center. I know where it is based off the map, and all that is right. That is what we're doing.
Yep.
Okay, and then I didn't see any lecture notes anywhere in like the course tab. Is there any like?
Yeah, I will be adding the lecture notes, and I actually am making hard copies of each of the lecture notes for you.
Okay, cool.
So
Those
in
are
your
my only
packet, when you guys get your lab, kit, you'll also get that. Did I tell you guys know the times, right?
I believe it says it
Okay. Good.
on the tab for it.
So no lab Zoom today?
So no, there's no labs until you guys get labs. So I'm sorry, that isn't true. Next week, you guys will have, you'll have, what is it called? Simulations to start you guys off on Monday. But
Okay.
after that, you probably won't do your first lab until. So I'll see you guys this weekend, or Friday, Saturday, or Monday.